Hello there. Today we're going to look at section 1.5. So hopefully you guys have completed all the assignments up to this point. You definitely should have done the 2 review sections before you do any of this stuff. If you haven't finished 1.4, that's okay. At least try to get it started, right? Because a lot of the techniques we used in 1.4 we're going to use in this. So this section is all about the definition of a limit. So it's sort of the rough definition. There's a more precise definition coming up. So I'm just going to briefly go over the PowerPoints. I'm going to do all the examples. The answers to the exercises are in the PowerPoints as well. So let's jump right in. I'll let you guys read all the definitions. The farther we go in this class, the more and more sort of words we add and definitions. So in the interest of keeping this video at around a half an hour and no longer, I'm not going to read all the definitions, right? But there are some things that I do want to talk about. And that a limit just means you can get very close to this number without ever reaching the number. That's basically what it means. And so this picture, anytime you have a definition in calculus, and later on when we see some theorems, they all go with pictures. So this is really the best way to think of this. That we have, if you just have some function, that here it's saying that the limit as f approaches a equals L. So that's what we're saying here. We're saying the limit. So, but it means really, 3 different things could happen. You could have the function itself evaluated at a equals L. You could have the function itself is not defined at a, or it's defined somewhere else. So here, it's defined at a different point. Turns out that the limit does not depend on the value of the function at a. It has nothing to do with that. Because what we're going to use limits for in the next 2 sections is to find tangent lines with limits. In the previous section, we looked at how to use tables to estimate a tangent line slope. And we noticed that you can't divide by 0. So it turns out that part of the definition involves that you don't need the function itself to be able to be evaluated at a particular value, right? Because that would cause a division by 0. So here there's a hole in the graph. Here there's a hole up here, but the point is defined at a different location, and here the function is defined at a. It turns out in all 3 of these cases, the limit is the same. So the limit just tells us that as you come in from both directions, that this number is getting closer and closer to some value that we call L, and coming this way, the y value is getting closer and closer to something we call L. And that's it. So this is not real precise. It's pretty much what you see is what you get. That's the way this section is. So let's jump right in and do an example. So this is very similar to what we did in the last section. It's not the same thing. We are not finding tangent lines here. We are just using that same concept of if we have a function and you can't divide by 0, can we still sort of figure out what's going on both sides of the function? In this case, here's our function, right? So let's type this into our calculator. And I'm going to do it the way I did it last time, right? There's always a lot of fractions. Okay, so let's do a square root. So we have x plus 25 minus 5 over x. And just as we did before, if you want to double check it, this has to be set on ask so that we can use our table. All right, so here's our table. So we're just going to plug these numbers in just like we did last time. Right, -1. Oh, one thing about graphing calculators, I don't know how well you guys know this stuff. You can't type in -1. Here, let me show you. Okay, so what did I do wrong here? Well, I tried to type this minus key instead of the negative. I have no idea why Texas Instruments built this into their calculators. But just make sure you're typing the negative sign, not the minus. I know that's weird, but that's how they do it. So negative 0.1, negative 0.01, negative 0.001. And it looks like it's getting closer and closer to 0.1. Great. Let's come in from the other way. If the other way is getting just as close, and if it's sort of zooming in on the same number, then we know that that's the limit. 0.001. So it certainly appears that the limit from both sides is 0.1. Now, we do want to graph the function, okay? So one thing I want to point out about these graphing windows, so this is just this goofy graphing window I had before. But let's say you don't know what graphing window to use, so you're like, oh, I'm just going to do negative 10 to 10, right? Isn't that everybody's favorite, negative 10 to 10? For those of you who have used these calculators before, you know what I'm talking about. Everybody loves negative 10 to 10. Well, let's see how helpful. And then delta x doesn't matter. You can put it back where it was. Like I said, I was goofing with it. There we go. That's fine. That's funny. I changed the x max. That's funny. Let's try it again. There we go. All right, so that's fine. That's where it defaults to. Okay. So let's graph this thing, see what happens, right? So we're not getting a lot of information here, ladies and gentlemen. So what did I do wrong? Well, here's the thing. When you use a graphing calculator, now we're not going to be doing a ton of graphing calculator work in this class. Early on, we do a lot. First week, we do a lot. After that, it slows down a little bit, but many of you are moving on to more advanced classes after this. So if you're going to take Calc 2, differential equations, stuff like that, you're going to need the graphing calculator. Physics, right? So what exactly is going on? What did we do wrong? This isn't telling us anything. Well, the thing is, we don't know anything about this function. So we do know a couple of points, right? If we go back to the table, we can see that these y values are all very close to 0.1. So maybe, and they're never negative, right? So maybe we should change the window, right? So what's the easiest way to change the window? So the way I suggest that you do it is you just look at the function and say, what is a reasonable domain for this thing? Well, we can see here that x is not allowed to be less than negative 25. So let's put negative 25 in over here. Yep, almost did it again. It's got to be negative. There we go. And then you say something like, well, we can go to 25 on the other side, right? Because there's no upper limit on x. There's just a lower limit on x. So that gives us an idea where x is going to be. Now, you want to use the zoom feature. So I don't know if you guys have ever used this before, but it's pretty cool. So it's this button right here, zoom. And you're going to go way down towards the bottom. I don't know why they hide it at the bottom. It's the only thing you'll ever use in here. Here it is. It's 0. It's called Zoom Fit. Hit enter. And what Zoom Fit does is it picks the best y coordinates for the x coordinates that you put in. Well, that graph looks a lot different than what we just saw in the previous graph, right? This graph is actually telling us something. Now, if you want a slightly better picture, go back to your window and just clean it up. So maybe we can go negative 30 to 30. So all I'm doing now is just expanding it a little bit to sort of center the graph up. So the y minimum here, it says it's like 0.8. I'm just going to make it 0. Y max, let's make it 0.3. Now it's going to be a little bit more centered. That's all, right? And so we kind of understand where it is now in relation to the axes, because it was sort of floating around before, right? So the reason we're graphing this is to make sure that the limit is in fact the same from both sides, right? We want to make sure that if you come in from, so here we're coming in from the left, doesn't matter what order you do it. Here we're coming in from the left. We can see that the y values are indeed getting closer and closer to some number. And coming in from the right, we can see that the y values are getting closer and closer to the same number. So this graph I made that in fooplot. It's in the syllabus. If you're ever doing any sort of thing where you need to have a really nice looking graph that you can print out and it's really easy to use, fooplot is the best one. So the idea here is that numerically we're told that the limit is 0.1, and the picture sort of reinforces that. Neither one is a proof. So if this were a test question, I would say use a table and sketch a graph, to show that this limit is believable or something like that. This is not a proof. We are going to do proofs later. For right now, we're still trying to understand what limits are, right? The function is getting closer and closer to some number on both sides. All right, let's move on to the next one. Oop, didn't mean to do that. Let's move on to the next one here. All right. So let me go back and just reset the window. Right, because these windows get goofy, right? So we're going to be doing another graph here. So let me just put it back, negative 10, 10, negative 10, 10. Oh, I messed up. There we go. All right, negative 10, 10, negative 10, 10. And then the y scale, the scale doesn't matter. Let's just make it 1. Okay. Yeah, that looks good. And let's put our new function in. So I just clear this out. So it's cosine of pi divided by t. Again, we're going to use x. You don't want to do the graph first. Students in the past have tried to do that. I've seen students on tests say, well, I graphed it and it looked like such and such. You can't. The graph can just confirm or deny what we get from the table, right? But you can't use a graph by itself as a proof. Okay, so we have the function put in. Let's go back to our table. Now, we don't want these numbers, right? Oh, yeah, actually, sorry, we do want these numbers. So that's why I picked this one. So I'm actually using the same numbers in the previous problem, right? Because we're getting closer to 0. So the table's already built in, right? We already have what we want. So you might think, well, it looks like the limit is 1. But here's the thing. Let's go back and look at the definition here. Look at what it says right here. The values of f of x tend to get closer and closer to the number L. These aren't really getting closer to anything, are they? It starts at -1, and then all of a sudden it's exactly 1. So this doesn't really satisfy the definition. Now, you could say, well, this calculator is just rounding to 5 decimal places, right? So if it's really 0.9999999, it's just going to round it to 1. So maybe it is actually getting closer. So we're going to have to do a graph to figure out what's going on. So we can see that this is a cosine function. So we know the range on cosine is -1 to 1, right? So we're going to go ahead and let's just do like 1 period, right? So let's go either -2 pi, let's go 0 to 2 pi or -pi to pi. It doesn't matter. You just want to see a nice picture of it, right? Right. So let's go -pi to pi. And then we don't need to go outside of -1 to 1, right? It's a cosine function, so it can't be outside of that. And let's see what it looks like. So I'm sure you're noticing that something terrible is happening here. And what exactly happened? Right? So again, I did this graph in fooplot. What is going on? What is this ugly thing? And why did our table tell us something different than what the graph is telling us. So some of you have already figured it out, what's going on here. So think about it. When you plug in -1, you're just getting, cosine of pi divided by -1, which is negative pi, right? So cosine of negative pi is -1. That's easy. But what's really going on here, right? Well, remember, if you divide by -1/10, that's the same as multiplying by 10. The period on cosine is 2 pi. So all of these numbers, if you keep dividing by 10 over here, when you have the t in the denominator, it's the same as multiplying this by 10 on the inside. So what you have is just a bunch of multiples of 10, and multiples of 10 are also multiples of 2. So multiples of 10 pi are also multiples of 2 pi. So what we're getting here is the numbers we picked to plug in just happen to form a pattern because of the construction of this function. So, does this satisfy the definition of a limit? We really can't tell looking at it. It does not appear to settle down on any particular value, right? If you look at the picture, it doesn't look like there's some number L that the function is getting closer and closer to. It just doesn't look like that. Now, maybe it is. So maybe we're not zoomed in enough, or maybe, if we look at a different area of the graph or something like that, maybe we see other things. But it doesn't look like that's what's happening. So what do you think we should say for this? Like, what would you say the limit is? Well, it turns out that if we can't find some L that settles down numerically in our table or in the graph, then that limit does not exist. And that's actually what we say. So I need you guys in the next exercise. This is example 2b. I want you guys to come up with your own numbers. Now, we've already graphed it, right? We graphed it in the previous problem. But see if you can come up with a pattern in the t's or some lack of pattern. Remember, there doesn't have to be a pattern. When we picked a pattern here, it artificially created a pattern here. Oops. But the idea is you want to find numbers that all get closer and closer to 0 from the left and from the right. Maybe you can find some way to do it so that there's no pattern. Even if there's no pattern, this should settle down in some way. So see if you can come up with something that will confirm or deny whether this limit exists or not. So I'll let you guys handle that one. Everybody will have different answers. You're going to have a worksheet that you can work on at home. There's a problem just like this on it. If you continue to have, or if you have any problems and then continue to have problems on the worksheet, you can always upload your work or email it to me and I'll check it just to let you know if it's good. So what's going on here? Well, what we've seen in the first two examples is that these tables maybe can't be trusted because there might be artificial patterns that we're putting in there by the numbers we're choosing. And the graphs might not be accurate. The resolution isn't high enough. Like, for example, maybe this limit does exist, but we just can't zoom in far enough or something like that. So what we're going to work on in the next couple sections is, well, actually, specifically section 1.6. So after 1.5, we're going to do 1.7 next. Then we're going to come back and do 1.6. You'll see why it makes sense to switch those when we get there. So tables cannot always be trusted and graphs are not always useful, right? That's what we came to the agreement. Sometimes they can, but sometimes they can't. We need methods that work all the time. So what's going to end up happening, guys, is that there isn't a method that works all the time. So sometimes tables are better, sometimes graphs are better, sometimes the algebra methods that we're going to see in section 1.6, sometimes those are better. So in 1.6, we'll work on better techniques for calculating limits. Not right now, but we'll do it later. Okay? So just for 1.4, 1.5, and what you'll see in 1.7 is they all use sort of similar methods. Now we're just going to take what we just learned about limits, and we're just going to break it into two parts. One-sided limits. limits from the left and limits from the right. So I'll let you guys read that. Make sure you memorize all these definitions because they're very, very important. But let's jump right in on the example, right? So this is actually what we're going to use. This definition is what we're going to use. That if the limit exists on both sides, which is what we did in our previous problems, then we say that the overall limit exists. So this is an if and only if statement, right? So if this happens, then this happens. And if this happens, this happens. So read that carefully. If you have to take separate notes, if you have to do flashcards on all these sort of fact sheets like this, great. But these videos really mostly focus just on the exercises, just in the interest of time. So this is a real easy example, really great example. This is actually called a Heaviside function. It's named after a guy whose last name happened to be Heaviside. It has nothing to do with how it looks. For those of you who are moving on to take differential equations, those of you especially in the computer science program, you're going to get a lot of Heaviside functions. So it's a really cool function that basically what it is as you come in from the left, as soon as you hit x equals 0, the function turns on. It's sort of used to model like flipping a switch. And once that switch is flipped, now the function is turned on. And so you can multiply a function by this Heaviside function and get it to turn on and off and things like that. So really useful in electronics. And anything that's based on electronics. So what is this limit? So as x approaches 0 from the left, so the minus sign means left. So let's see. We're coming in from the left, but we can see clearly that the y coordinate of this function is fixed at 0, right? And that's what it says right here, right? If t is negative, oh, sorry, these have x's. That's a typo. These should all be t's. Sorry about that, guys. I never find typos till I actually make the videos, right? So as we come in from the left, when t is negative, the y-coordinate is 0. So the limit is 0, right? Because it's getting closer and closer to 0. As t gets closer and closer to 0, the y-coordinate, even though it's already 0, it's as close as it can get, but it's not changing, right? So that limit is, in fact, 0 coming in from the left. And from the right, it's just 1. So it's coming in from the right, which makes it 1. Right? And that's what we put here. I did the same thing here with the x's. Sorry about that. I'll fix this in before I upload it. So hopefully when you guys are following along, it'll be t's in your PowerPoints. Right? So on the left side it's 0. On the right side it's 1. So what does that mean? Let's go back and look at our definition. If the left side limit is different from the right side limit, then the limit does not exist. So we've seen two ways a limit can fail to exist now. One is when it gets super wiggly, and the other one is if for some reason, as you approach a number, if the limits are different on both sides, and that's actually what happened here. So just as a little bit of shorthand, just to save yourself some trouble, if you want to write the limit dne, like it equals dne, that's totally fine by me. You don't have to write a bunch of complete sentences normally in a class like this. And so I just call it the overall limit, right? It's the limit from both sides. So if a function is super wiggly or different on both sides, then the limit does not exist. It has to exist, and it has to be the same on both sides. Next up, we have infinite limits. So these are just plus or minus infinity. And all this means is that the value of f of x, so the y-coordinate, can be as big or as small as you want as you get closer and closer to this number a, whatever it happens to be. Right? So that's what this phrase arbitrarily large means here. It just means as big as you want for infinity, and for negative infinity, as small as you want. This is just a shorthand notation, right? Infinity is not a number. Please don't go around telling people I told you infinity is a number, because I didn't. It just means that we are finding some sort of vertical asymptote, right? That's all it means. So You guys probably remember vertical asymptotes from college algebra when you did rational functions or algebraic functions. Same sort of thing here, right? It just means that the function grows without bound as x gets closer to some number. So we're going to just do another one of these, right? We're going to put this in our graphing calculator. We're just going to do the same thing and see what happens. And we're going to estimate the value of the following limit. So just type everything in, just the way it looks. So let me clear this out. So we have x plus 7 over x minus 5. Okay, and we want to get closer and closer to 5. So we need new numbers, right? So let's just use what we've used in the past, right? Yeah, so let's do 4 and 6. I couldn't remember where I started. Let's do 4. It doesn't matter if you start on the left or the right first. So 4, 4.9, just kind of the stuff we've been doing. And then we'll come in on the other side and we'll go 6. 5.1. 5.01. Come on. 5.01. There we go. And 5.001. Right, and that's what we got. That's what we got on the table over here. So what's going on? So let's look at the behavior and see if we can figure out what's happening. As we come in from the left, look what happens to the function. It is growing without bound. That means that there is a vertical asymptote at 5. Now, we're only looking on the left side. We don't, until you go over and look at the right side, we don't know what's going on over there. Remember, you could have a vertical asymptote on one side and not on the other side. It actually happens all the time. So let's look on the right side now. So here we can see when we plug in 6, you get 13, and again, it's growing without bound. But these are different limits. These are negative numbers. So the limit on the left side is negative infinity because of the vertical asymptote. But on the right side, it's the same vertical asymptote, but the function is stretching the other direction, right? So, don't know what viewing window to put in, so I'm just going to go back to negative 10 to 10. Don't worry, I'm not going to graph every function the whole semester. Right? And this is what we would expect to see. Right? So x equals 5 is like right here. And you can see clearly that it's going to negative infinity from the left and from the right going to positive infinity. So both limits are unbounded, but one's negative and one's positive. So on the homework, make sure you're paying extra close attention on the homework. If it has a little minus sign here, that means from the left. Even if it's unbounded, you still write negative infinity. That means that it's unbounded. That means vertical asymptote. It's just a shorthand way of writing vertical asymptote, right? Same thing here. And later on, we're going to see other types of limits that also have infinities, but they're not vertical asymptotes. So this notation does a lot of stuff for us. Here, if it has a plus sign, that means from the right. These numbers are growing without bound. But because they're different on both sides, that means this overall limit does not exist. Now, you might be thinking, well, couldn't we just get that from the graph? Sure, but remember, how do you know that you're zoomed in correctly? We saw a problem earlier where not zooming in, actually we were zoomed in too far, right? We needed to actually zoom out in the x direction and zoom in the y direction. So the graphs give us like sort of a skewed and limited view of what's really going on with these functions, right? So just be careful. All right, let's do the last one here, limits using graphs. So you can see that this graph has all kinds of stuff. right? It's got open circles, closed circles, vertical asymptotes. It's got everything. So let's see if we can figure out what's going on here. All right, so the limit as x approaches -2, so there's no plus or minus, right? The negative is on the front, but on the upper right side of the 2, like this has a plus right here. If it doesn't have that, that means it's a two-sided limit. That's what it means. We have to check both sides. So here's 2. Here's -2 right here. So it looks like the function as you come from the left is getting closer and closer to 3. And as you come from the right, it's getting closer and closer to 3. Remember, it doesn't matter what is happening at the point. It only matters, are both y coordinates getting closer and closer to the same number? That's all that matters. So we would say that the limit here is 3. Let's look at the next one. The limit as x approaches 4. So 4 is right here. So on the left side, as we get closer to 4, it grows without bounds. That's a positive infinity. And from the other side, it also grows without bound. The same direction, also positive infinity. So because those two limits are the same, then the overall limit is in fact positive infinity. And let's look at these two individual limits. So here we just have a limit as x approaches 1 from the right. So here's 1. Coming in from the right, the function is getting closer and closer to -1. So the answer to that question is -1, because the y-coordinate that this is getting closer to as we come in the x direction, it's coming up to -1. And last but not least, there's 2 more. As x goes to -1 from the left, so we're getting closer and closer to -1, and x is getting closer to, getting closer and closer to 1 from the left side. X is getting closer and closer to 1, and the y-coordinate it's approaching is 1. It doesn't matter that this is an open circle. It does not matter. We don't care what's happening at the point 1. So what we had here is this limit was -1. This limit was +1. That means the overall limit does not exist, right? So that's just a nice, easy shorthand way to write it. Okay, so that's basically it for this lecture. Hopefully it wasn't too long, guys. If you need extra practice, here's some more odd problems out of the book. The ones that I think are helpful. Some of them look just like your homework, some of them don't. Media index for this section, all of the entries are very good. Go ahead and check them all out. And the homework tutor covers a bunch of these problems. It covers so many of them, I didn't even want to write the numbers down. It covers about 20 of them. There are step-by-step instructions how to do about 20 of these problems. Can't beat it. Go ahead and give it a try if you need extra practice. There's also a worksheet that I posted that has answers available. If you have questions about it, just give it a shot. It's more practice using the techniques that we've built in the last 2 sections, right? With our MPQ function from 1.4 and with our limit concept here in 1.5. So that's it for this set of notes. If you guys have any questions, you can email me or post things on the discussion forum. And, take advantage of the resources available. And if you have any questions, let me know. All right, see you guys next video.